Metals are crystalline materials. There's rare cases where they could be amorphous, but generally speaking, metals are crystalline materials. So by heating a metal, you could change the crystal structure of that metal and get certain desired characteristics, such as hardness. Most people are familiar with Rockwell hardness, for instance. So you do a transformation, a crystalline transformation, and then you try to lock that in, or you try to cool it so it transforms more to a different phase and lock that phase in. So you could get characteristics such as hardness or toughness. In some cases, although we're not involved really in salts to do that, you could also infuse materials into the surface of the metal and form what's called a case. So you could have a nitrogen case, you could have a carbon case or a carbonitride case. And these types of surfaces could give lubricity too. But generally speaking, what we're discussing with today are to do what's neutral hardening and then tempering back to get in a specific crystal structure, to get a specific characteristic out of a given metal. Salts are blends of salts, common salt. For instance, what's called a high heat salt is a blend of potassium and sodium nitrate, typically. It could also have, if it's a very high melting point salt, you're working at higher temperatures, you put barium chloride in there as well. So you have potassium, sodium, and barium chlorides present in one salt. That's a neutral salt, and that's typically called a high heat salt as well. And then you could have the other salt, common salt, is what's called a tempering salt. And a tempering salt typically operates at temperatures below 1,000 degrees, but at 50 to 100 degrees above the melting point. And tempering salts are blends of sodium nitrite, sodium nitrate, and potassium nitrate. There is one salt that's sold for aluminum heat treating that's just sodium nitrate and potassium nitrate. So you have your nitrate salts, which are your tempering salts, and you have your high heat salts, which are your chloride salts. And what the salt is, it's a dry powdered blend, but you heat it to its melting point. And then it becomes a liquid. It's a melt, just like as ice melts and you have water, same thing with the salts. The methods that are used to heat treat metals are salts or furnaces. In other words, you could have parts on a conveyor belt going into a high heat furnace, and it's just air that's around there to heat the parts. And the parts will come out, and then you do what's called a quench to cool them down to try to lock in a structure, or cool them down and then heat them back up to a range, typically between 300 and say 800, and temper back the metal. That can be done on a lot of parts that are fasteners, for instance, small parts. Where salts are really used, or salts are used where you want very little distortion. As you know, if you heat something, or you may know, if you heat something and you cool it rapidly, it could distort. Salts, because they're relatively dense liquids, lessen the amount of distortion during the heat treating process. So therefore, salts are used on things such as gears, precision gears, lawnmower blades is a huge area where salts are used. And primarily for distortion purposes. And really what salts are doing when you look at a molten salt, it's used for two purposes. It's used to add heat to a part, or used to take heat away from a part, such as in a quench. And if you remember thermodynamics, heat flows from hot to cold. So if you have a hot salt, the heat flows into the part to heat it up to a temperature to neutral harden it, and then that could go into a quench, and the salt is cooled, and the part as it goes in, the heat goes from the part back to the salt, and the salt will absorb heat to a much greater extent and much quicker than, say, air would if you did an air quench, which some people do out of furnaces. I answered that, and actually in the last question, I jumped ahead a little bit. The three basic, just to summarize again, there's three basic types of salts. Tempering salts, which are the salts that operate, say, from 300 to 900 range. And those are typically used either to heat a part up if the part does a phase transition in that temperature range, or to cool the part down to that range and lock in a crystal structure of the part. Then you have your neutral salts. The neutral salts are typically used above 1,000, more typically used in the range of 1,500 to 1,800, maybe as high as 2,100 degrees Fahrenheit for the neutral hardening. And then a third salt are the case hardening salts that you will see out there. You don't see them used as frequently anymore, but if you have a part where you want low distortion, yet you want to do a carbon or a nitrogen or a carbon-nitrogen combination case on the part, which is a very thin layer, you could use your carburizing or case hardening salts. So there's really three classes of salts that are still out there being used. They are, if they're nitrate-based salts, nitrite-based salts. The difference between the salts are the ratios, and the ratios determine what the melting point is. So there's a salt that has it's a eutectoid mixture. It's a very precise melting point. It melts at 275. Then you could have salts such as the one that's used for aluminum, which is just potassium and sodium nitrate, that melts at 420 Fahrenheit. So it's really, all the nitrate-based salts contain the three basic nitrogen species, which are the sodium nitrate, the potassium nitrate, and the sodium nitrite. You can, in theory, mix them together, but you're going to alter the melting point because your ratios are going to change. So they're compatible, they can be mixed, but they don't give you that precise melting point that's important. And it also changes the heat absorption or the heat transfer characteristics of the salt as well. High heat baths react, because they're so hot, they react with CO2 in the air. So you can imagine you have this molten solution of salts. It's glowing red. It's reacting with CO2 to form carbonates in the bath, but it also forms oxides in the bath. And what happens when you get those is it can interfere with the heat transfer. It could lead to some difficulties with the metallurgy of the part. So what you have to do is you have to rectify to remove those oxides. And that's typically done with pellets, or it could be used in days past, people would bubble methyl chloride gas through a salt to rectify it. So what the salt is, or what the rectifier pellets are really doing is it's eliminating those oxides that are built up in there and neutralizing the carbonate. The pellets generate ammonia effectively in the salt. So you want to add the pellets in a basket on the corner of the tank. And of course, with any rectification, you do the rectification when work is not in the bath. You also want to do, as you're evolving ammonia that reacts to neutralize the carbonates and react with the oxides, you want to make sure that's done in a well-ventilated area as well. So you get none of the gases that may be formed escaping into the work environment. The best way to desludge a bath would be to cool it down as close to the melting point as possible, say within 50 to 100 degrees of the melting point. And what you're doing with desludging, and you see it more with the tempering salts, because you'll come out of a high heat bath, that's the chloride bath, with salts that have melting points of 1,000 degrees or higher, and you go in to do a tempering bath that's operating below that melting point, and the salts, the neutral salts will come off in the tempering salt, and of course, they're not melted at the temperature of the tempering bath, so those salts will come out and they'll precipitate out. in the form of sludge. So what you do is you cool that tempering bath down to, if it's a 275 melt tempering bath, you cool it down to say 350 Fahrenheit, and then you go in and you ladle the sludge that's falling out. It's almost like snow falling. Imagine your tempering salts, the atmosphere, the chloride salts, the snow that falls down and accumulates at the bottom of the pot, and you take it out. Contaminants that are dragged into high heat baths, say the work isn't cleaned quite well enough, or there's a lot of grit and grime or particulate matter on there. You could also get these sludges forming in a neutral bath, the high temperature neutral baths. And the same thing, you cool it, say the bath, the salt at a melting point of 1,000, you'd cool it down to maybe 1,075, and then slowly and very carefully, of course, go in and try to ladle out from the bottom of the salt bath the contaminant to get them out. We routinely do salt bath analysis for customers. In some cases, it's paid for. In some cases, it's not. But we have the capability to do both the high heat neutral salts and the tempering salts. There really isn't much difference. It really is all predicated on what temperature you want to operate at. With the exception of the salt that's used on aluminum, that salt is very specific because you don't want nitrites in a salt that's used on aluminum. So it really depends on the factors that come into play, of course, are the cost of the salt, sodium nitrite being the most expensive ingredient that's typically in there, but it's also the ingredient that gives you a lower melting point. I tend to recommend, over the years, I've recommended a 275 melt point. It's a very precise melt point. It gives you an operating range up to 1,000 degrees Fahrenheit. The salt could be used for a lot of things. If you want a less expensive salt, you could go to a 300 melt point salt and use that instead. But generally speaking, there's not a lot of difference in the heat absorption or the heat conduction characteristics of a salt when all's really, of the tempering salts when all's said and done. We do the testing down in Inman, South Carolina, our Inman facility. So they'd be sent into the attention of Dr. Douglas Patton. Doug does all the salt analysis for us.